Hi there. My name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in the last lecture of GPU programming for video games, we looked at a scriptable render pipeline in Unity that implemented forward rendering. In this lecture, we'll look at a scriptable render pipeline that implements deferred rendering. This lecture uses some code snippets from the previous lecture, and it leverages some ideas from that lecture. So I'm going to assume that you've seen that previous lecture. So if you haven't seen it, go watch it and then come back here. To run my demo code, go to my CS-ECE 4795 GitHub page, scroll down a bit, and you'll find GPU23 SRP deferred.unity package. Go grab that. Before we load in that Unity package, we want to go to the package manager, make sure we have the Unity registry selected, and load in the core RP library. Now, if we wanted to do something with a high definition render pipeline, we could go get that. Or if we wanted to do something with the universal render pipeline, we could go get that. But we're developing an entirely custom scriptable render pipeline, so we just need the core RP library. And let's install that. Okay, let's load in this demo. And here we'll look at the deferred rendering scene, and we don't actually see anything. Of course, it's still trying to use the built-in pipeline, and we have a new special custom pipeline that we need to use. So let me go up to, let's see, it's edit, right? Edit project settings, and we do a couple things. First thing, always go to player, make sure this is set to linear because linear is good and gamma is bad. And we want to go to graphics and select this my deferred pipeline. Okay, let's change the pipeline. And now we can see our things. And here we have our scene. Notice that the scriptable render pipeline we have does work in the scene view. Let's press play, and you can see I have a little script that moves one of the lights back and forth. I have 4 lights in the scene. Unfortunately, these don't have the little light gizmos that you're used to seeing in the scene view. That requires some additional draw gizmo code that I haven't included here, just because I wanted to keep the amount of code I'm showing you relatively small, because even though I'm trying to keep the amount of code I'm showing you small, it's still a lot of code. Now in the forward rendering demo we did, we had one shader that we called mylit that could handle both opaque and transparent objects. Here, we need 2 separate shaders, one shader to handle opaque objects and a separate shader to handle transparent objects, because deferred rendering can't really handle transparent objects. So we're going to deal with transparent objects using usual forward rendering, and we'll handle opaque objects with deferred rendering. So mylit opaque is actually going to just fill in the GBuffer values that include the albedo and the normal information, whereas my deferred is what's actually going to run through all of the lights and do the lighting calculation based on the GBuffers that were filled out by this mylit opaque shader. If you look in the materials folder, you'll see I have 3 opaque materials of different colors and 2 transparent materials of different colors. But I also have 2 special materials, one called CopyDepth and one called myDeferred. These are special materials used in the deferred rendering process, and these aren't materials that you would actually assign to a 3D object directly. The CopyDepth material uses the CopyDepth shader. I'll talk about what that does a little bit later. And the myDeferred material refers to the myDeferred shader. Notice that the lit shaders are part of a GPU23 deferred menu in the shader list. But the CopyDepth and the myDeferred shaders, those I put in a menu that I called GPU23 deferred utility to try to indicate that these aren't things that we actually put on objects. They're handling other aspects of rendering. So let's take a look at the myDeferred pipeline asset. We have dynamic batching and instancing that we can turn on and off. These are associated with various optimizations Unity can do behind the scenes. I'm not going to worry about the details of these here. Now, there is this slot here to assign the CopyDepth material, and there's a slot here called deferred material that we're assigning this myDeferred material. And basically, these are just materials that have those associated shaders attached to them. They don't really have any parameters. Now, I had this pipeline available already in the Unity package. If I didn't, we could go to the assets here and click on plus to add an asset, go down to rendering and select my pipeline. Now, this isn't something built into Unity. We have to write code to create this menu item. All right, so let me select my pipeline. And just for fun, let's go to the edit menu, go to project settings, and see what happens if we try to switch to this new pipeline asset. Aha, everything goes away. Oh, and it's having some sort of weird freak out. Okay, so what's going on here? Well, if we actually click on the new asset we created, we see we don't have the correct materials installed here. So there's just weirdness going on. We need to change this to CopyDepth, and we need to change this to my deferred, and now everything works. Now, just for consistency with my original demo, what I'm going to do is I'm going to delete this particular asset and everything should disappear. And let me go set that back to the original, my deferred. There we go. So I have 3 objects in back that are opaque. I have 2 here in front that are translucent. And now it's time to take a look at some code. Some snippets from the code I'm about to show you are from this tutorial by Catlight Coding, but the bulk of it is from this tutorial by Peter Bay-Bastien from his SRP from Scratch repository here on GitHub. I did rearrange the code. If you look in the assets folder here, some of the stuff is from this Scratch library, the scratch.hlso file that I basically pulled out and pasted directly into the main part of the code. And the main part of the code you can find in Solutions, Part 5 Deferred. Because the Mylit opaque shader is dealing with opaque objects and not transparent objects, we're going to set the render type tag to opaque. And the job of this shader is not to compute the final color that the player sees. The job of this shader is to fill out the GBuffer information, namely the albedo and the normal map information. So we're going to use a light mode tag of GBuffer. We'll come back to this point later. Much of the rest of this is the same as what we had in the forward rendering demo. We have this weirdness associated with the GPU instancing capability of Unity. This is an optimization Unity can do behind the scenes, where sometimes it will have to take this Unity object-to-world matrix and do something weird with it. So instead of using this nomenclature, we're going to use these capitalized defines. The rest of this is the same as what we had in the forward rendering demo. This setup here is also the same as what we had in the forward rendering demo. We have some variables associated with the lights, and these are variables that we need to actually set in the C# code. This isn't like the case in the built-in pipeline where Unity handled this for us. We have the data structure associated with going from the application side into the vertex shader, and then we have another structure associated with going from the vertex shader into the fragment shader, where this kind of information here is getting interpolated. But we are going to need a new kind of structure. This is going to be the output of the fragment shader. So RT0 is going to handle the albedo, and RT1 is going to handle the normal. So this is something new. We're used to fragment shaders explicitly returning the final color that we're drawing onto the screen, and usually there's also ZBuffer being written, but we don't generally have to think about that ourselves. The vertex shader has all the standard stuff, and in fact, this code is exactly the same as the vertex shader in our forward rendering demo. The clip position that we're computing here isn't explicitly used by anything in our fragment shader, but of course it's needed to figure out what pixels are actually being painted on the screen and what ZBuffer values to write. And then there's not much to the fragment shader. We start with this bit of Unity magic, this Unity setup instance ID. This has to do with GPU instancing. You can take it on faith. We have normal information coming in. That's interpolated, and there's no guarantee that's going to be normalized, and in fact, it probably won't be, so we need to normalize it. For the albedo, we're just going to use the color that's set in the inspector. You can, of course, add textures and other fancy things to this. And then basically all we need to do here is output that information. So our GBuffer output type here is going to have RT0 set to the albedo, where we'll stick 1 in the alpha coordinate here because it's an opaque object. And for RT1, we'll encode the normal information. Remember, the XYZ of a normal may be -1 to 1, so we'll divide it by 2 and then add half to that to scale that to be between 0 and 1. But we'll have to remember to expand it back out later. And that's it. Later in this lecture, we'll look at the C# scriptable render pipeline code that actually sets up these render targets, runs the rendering routine to render the objects to them, and then uses the information in the render targets to actually create the final colors. The lighting calculations that formulate those final colors are computed in this Deferred shader. This deferred rendering pass is a spiritual cousin to a post-processing effect. We're turning Z-write off because the Z-buffer is no longer relevant, and we're using Z-test always, which means we're always going to write to the color buffer without doing any sort of Z-checks. And similarly, backface culling is no longer relevant, so we turn that off. So we have the same sort of boilerplate having to do with GPU instancing and the definition of the combined view projection matrix, and the object world and world to object matrices are the same. And for this to work, we're going to need some inverse matrices. Here we have the inverse of the projection matrix, and here we have the inverse of the view matrix. So we have the same data structure for the lights as we had in the forward rendering shader that we did earlier. And now we define some textures. So we're defining GBuffer0 and GBuffer1, but the style we're defining this with is a little bit different than what we've used before. Previously, we used tech2D, where tech was in lowercase, and here we didn't have a separate data structure associated with sampling from the texture. But in this new style where we use this texture 2D macro, we also use the sampler macro, where we prefix sampler to the name of the texture. The sampler contains information like whether you're using nearest neighbor interpolation or bilinear or whatever. If you want it, you can take the name of a texture and add underscore texel size to it, and that will give you certain bits of information. So Z and W contains the width and height of the texture in pixels respectively, and X and Y contain 1 over width and 1 over height. Our code is going to use the X and Y fields. We're also going to need Z-buffer information, so we also declare camera depth texture. I don't know why they use this underscore float here. Last time I looked, it seemed like texture 2D underscore float just mapped to texture 2D, but there may be something subtle that I'm missing. So there's not much to the vertex shader. It's just like what we had in post-processing because we're just drawing a rectangle to the screen. Notice we didn't define any structures for passing information into the vertex shader because we don't have normals or texture coordinates or stuff like that. We just have a position in object space represented as a float 3, and this is going to spit out a float 4 that represents a coordinate in clip space, and that float 4 is input into the fragment shader here, and we'll call it position CS to indicate that it's in clip space. Now, the fragment shader is going to return a float 4 that's a color. Now, I'm going to confess that in the blitting operations that we look at later in the C# code that runs this particular shader, I don't really have a good sense about what the actual coordinates of the rectangle going in are, or what's in these particular matrices, or how any of this actually maps to what's going on in this clip space. But there's something about this that feels very weird to me, because ultimately, to get this to work out, you need to multiply by this texel size, and that's 1 over width and 1 over height. So after you do this multiplication, you wind up with something that goes from 0 to 1 in U and 0 to 1 in V. So the clip space here doesn't really operate the way we usually think about clip space for 3D objects. There's something else going on. But let's just take it on faith that if we run through all these operations, you get something where you can look up things in textures here, GBuffer0, in order to get the albedo by looking up this UV coordinate. And by looking in GBuffer1, By looking up in this UV coordinate, we can get the normal, but we have to remember that normals go from -1 to 1, whereas colors go from 0 to 1. So we need to take that 0 to 1 and multiply it by 2, and then subtract 1 to get something that goes from -1 to 1. So the rest of the code here where we loop through the lights and do the diffuse lighting calculation is the same as what we had in the forward renderer, with the exception of the fact that in order to get the position in world space, to do the lighting calculation in world space, we need to reverse engineer that from whatever the UV texture coordinate is and our GBuffer information. That's performed by the SampleDepthAsWorldPosition function, and we'll take a look at that now. So the position NDC, that stands for a position in normalized device coordinates. And here that corresponds to our UV that's going from 0 to 1. There's potentially some weirdness having to do with particular hardware things and API things that may involve us needing to flip that upside down. Luckily, Unity takes care of that for us. So we then sample the depth texture, and I think the .r here isn't necessary because when I check the HLSL support library, it looks like sample depth texture just maps to a Tech2D lookup with a .r in it already. There may be some particular hardware or API weirdness where we need to flip the Z coordinate around, and it looks like the resulting device depth runs between 0 and 1, but the remaining computations expect us to be using an OpenGL convention where the depth runs from -1 to 1 versus the 0 to 1 used in Direct3D. So we have this code here to map ranges from 0 to 1 to -1 to 1. So we run this compute view space position function in order to take the available information and return a position in view space. And then we can use the Unity camera to world matrix to turn this view space coordinate back into a world space coordinate. This matrix is the inverse of the view transformation. And notice that we need to add a 1 here for the W coordinate. So the first thing this compute view space position function does is it runs this compute clip space position function, and there's not much to it. Device depth is already between 0 and 1, so for the third coordinate here, it can just return device depth. However, the normalized device coordinates run between 0 and 1, so we need to multiply by 2 and subtract 1 to map those NDCs into a coordinate running between -1 and 1. And there may also be some API hardware weirdness, whatever, where we have to flip Y upside down. So we can take those points in clip space and multiply them by the inverse projection matrix to get the positions in view space. And because life is confusing, we need to negate Z. I find it's better not to think about things like this and just trust the code examples. Now, we still want to correctly handle perspective projection, but that's not being handled by division hardware, handled when we render to the screen, so we need to do that ourselves by dividing by W here. Now, I just spent over 3 minutes talking about all these coordinate transformations. If you didn't follow all of that, that's okay, because frankly, I didn't either. The main thing to note is that we can take this SampleDepthAsWorldPosition function, plug these things in, and it will magically give us the coordinates we need in world space. For the purposes of this class, you can take that on faith. Before we go on, I think it would be cool to be able to visualize the GBuffers. Let's go to our deferred lighting shader, and let's see. Let's take this last line here, and instead of returning the diffuse light times the albedo, let's just return the albedo. So I'm going to take out diffuse light here. So here we see the albedo of our opaque objects. Remember that the transparent objects are being handled in a separate forward pass, so those are the same. Now let's visualize the normal information. Let's see, here we scaled it to be between -1 and 1. Let me just take this bit here and paste it in here. So we'll look at the compressed normal information that's going from 0 to 1. Okay, here we have the compressed normal information. And actually, I think It might be easier to see what's going on if we use the -1-to-1, where we just truncate everything below 0 when displaying it so it shows up as black. So let me try taking all of this here and replacing it with just normal WS. Okay, so red indicates the X normal, green represents the Y normal, and blue represents the Z normal. But remember, this represents the normal in world space, not the normal in view space, which is the kind of normal we typically use in a post-processing effect. And we should be able to visualize this camera depth texture. That's just a float. So what I'll do is I'll go down here and let's say float 3111 times that. All right, camera depth texture. Wait, that won't work. That's the actual texture. I need to do a texture lookup. So that's something like texture 2D. Let's see. Texture 2D, what's the calling structure? Sample texture 2D. So let's do sample texture 2D, and we'll need that in the first argument, and then we'll need sampler that underscore camera depth texture in the second argument. Let's see, so let's put that here. And actually, do we need underscore sampler or is it just sampler? Right, it's just sampler. Then I need comma UV. Okay, I think that should work. Okay, so that's not very illuminating. Let's see if I zoom in. There we go. There I zoom in. Here I zoom out. Zoom in. Zoom out. Let's zoom in over here. Zoom. All right, so when I zoom in, it gets closer. So I'm seeing that as a 1. And it looks like when we're further away, then that's like a 0. Okay, so things are weird in terms of how I was expecting that to be. I was expecting it to be white further out, but it's whatever it is. That's kind of a hardware thing, and it switches things around as needed internally. Okay, so that was all about opaque objects. What about transparent objects? Well, transparent objects have to be rendered using forward rendering. We can't render those with deferred rendering. So the code for handling transparent objects is the same as the code that we had for our forward renderer, except we set the Z-write and blend modes here directly instead of setting those in the inspector. So notice that we're using Z-write off, so we're not writing to the Z-buffer when handling transparent objects, but we are still defaulting to running a Z-test, so transparent objects that are behind opaque objects won't be drawn. This time we'll explicitly set the light mode to forward, but other than that, the rest of this code is exactly the same as all of the code that we had in the previous lecture where we did forward rendering. So you can go back to that lecture to see a description of this code. We're going to need one more utility shader, and that's this CopyDepth shader. I'm not 100% sure why this is actually necessary, but let's just go with it for now. I'll talk about that more later. So most of the code for this is just the kind of boilerplate we've already seen. And really all this shader does is take our camera depth texture and just spit it right back out. Because apparently we will need to copy this camera depth texture into the actual Z-buffer associated with the actual camera that's being rendered. I'm not sure why, but we'll talk about that later. Okay, 20 minutes in, and we're finally getting to some C# code. I have no illusions about what making such a long video does to my watch time, but I like each lecture to be self-contained, and the C# code doesn't make any sense without seeing the shader code. And seeing the shader code makes no sense without seeing the C# code. So this is the script associated with our render pipeline asset, and it has our variables for dynamic batching and instancing that we looked at in the forward rendering lectures. We also have a couple of instance variables to handle the CopyDepth material and the deferred material. To keep the code simple, these are being initialized to null, and you have to manually assign these in the inspector. If this was more along the lines of production code, we would include some scripting in here to assign these automatically, but I wanted to keep the code short. And here we have the Unity-ism that allows this script to be run from the Add Asset menu in Unity. So our code is making use of render textures. Those are bits of video memory that we can write to using one of our shaders, but then take that chunk and interpret it as a texture to use in another shader. We will often refer to render targets with render target identifiers, which provide a consistent interface for various parts of your code that need to deal with render targets. This is the biggest and most complicated chunk of C# code we've looked at all semester, so I'm not going to go through every single line. I'm just going to point out the most interesting bits. Here we're creating an array of render target identifiers associated with our two GBuffers. Here we're declaring the variables for our CopyDepth material and deferred material in our render pipeline object. Note that these aren't automatically assigned to what we had in the render pipeline asset. We'll need to do that in code. And here's that code. Our constructor takes the materials from our pipeline asset and our GPU optimization variables from our pipeline asset and copies that information to our local variables. We have two render functions. One takes in an array of cameras and just loops through the render functions for an individual camera for each of those cameras. So that's what we need to focus on. Okay, here's our main render function. We have this bit of code that we talked about last time that lets our scriptable render pipeline work in the scene view and not just the game view. The rest of the code here is basically what we had in the forward scriptable render pipeline demo from the last lecture. And this figures out information about what objects can be viewed by the camera. Remember that our rendering code made use of two GBuffers, GBuffer0 and GBuffer1, as well as this camera depth texture. Here, we're defining references to those textures on the C# side. And we're also creating some render target IDs that will let us refer to those textures as render targets. So you give the constructor render target identifier a texture, and it will spit out one of these IDs. Now, I don't necessarily have to put a property number here. I don't have to use these kinds of property numbers at all. I could just put a string here. I could put underscore GBuffer0 string, but using the properties is a little bit faster. We're doing the same kind of setup for this color RT buffer, and that's what we're actually going to write colors to from our deferred rendering shader. I'm not entirely sure why we need it, just as I'm not entirely sure why we need this camera depth texture. We'll see a little bit later, we'll need to take this information and copy it to the final texture buffer used by the camera that's actually shown to the player. And we need to do the same thing for the ZBuffer info. I'm not sure why we can't just write these things directly. If you have some insight on that, let me know in the comments below. Okay, so we need to send some commands to the GPU. In the last lecture, we allocated a command buffer using the new keyword. Here we're getting one by sending the command buffer pool class a message for the static method get, and I have no idea why you would use one approach over the other. If you have any insight about that, please leave a comment below. So we need to tell the GPU to allocate memory for our various render targets, and we do that with this getTemporaryRT method. In addition to giving it a render target identifier, you give it the width and height that you want, and here that's going to be the width and height of the camera. The fourth argument here is the bit depth of a depth buffer. The only place this is relevant is in the fourth command here, where we want a depth buffer of size 24, and we can just stick zeros in here as dummy values because it's not relevant. We're using filter mode.point because we want to process each individual pixel and not do anything weird like bilinear interpolation. All of our various render targets match each other in terms of their width and height. The last argument is the data format. So .argb32 indicates that we're using 8 bits per channel. That's what we're using for GBuffer0 that stores albedo color information and our final color render target. Now, for GBuffer1, which stores normal information, we're using something else. We're using this weird ARGB2101010 format. So this uses only 2 bits for alpha, but it uses 10 bits for R, G, and B. So that's 2 additional bits of precision for the RGB channels over ARGB32. And that's helpful here since here RGB don't represent colors, they represent the X, Y, and Z of normals. And for our ZBuffer render target, we use the .depth format. So now we're going to take our GBuffer render target IDs and assign them to our GBuffer RTIDs array. And that's what we're passing to this set render target command. And this will mean that the next time we draw objects, we will run a shader that can write to these GBuffers. And instead of the Z information going to the usual ZBuffer for the main camera initially shown to the player, it's instead going to write that information to our depth render texture. Okay, so we then clear the render target. The first true says that we want to clear the depth buffer, and we could give this a 4th argument if we wanted. That would indicate what we want to clear it to. This defaults to a 1 if you don't have something here, which is basically all the way back. It's the furthest you can get. The second true says that we want to clear our color buffer, and that's all of this stuff in here, and we're going to clear that to black. Notice, as a matter of coding style, Peter Bastian, who wrote this code, put these lines inside these curly braces. That creates a local scope. And in later bits of code, he puts code in a different set of curly braces so he can reuse this var command structure. I'm not sure why he did it like that, but he did it like that. Okay, so the code that starts drawing opaque objects looks like the code for drawing opaque objects in the forward rendering demo we looked at in the previous lecture. However, we have one main difference, which is we have to do this in 2 passes. In the first pass, we need to fill out the GBuffer. So we're going to use drawing settings using this GBuffer shader tag ID. So that's going to grab shaders with this light mode equal GBuffer tag. Remember that shader code is going to fill our GBuffer render targets with albedo and normal information. All of this code for setting up the light information in our shaders is basically the same as what it was in the forward rendering demo we looked at last time, with the minor difference that we're using this command buffer pool.get style. Okay, now we need to run this bit of shader code that takes the albedos and the normals from the GBuffers, and that does all of the lighting calculations. That's done here in the split command. So blit takes a source and then writes to a destination according to this material in the 3rd argument. And that 3rd argument here has this deferred material with that shader that does all those lighting calculations based on the albedo and normal information in the GBuffers. Now this calling structure here is a little bit misleading. Indeed, color RTID is the render target that we're writing to, but this first argument here, you could put any render target ID in this spot. This isn't used. Your first argument is considered the source, and it gets plugged into something called underscore main tech in your shader. But there is no underscore main tech in that shader. So this first argument here is just a placeholder. The real information sources for our shader here are these render textures, the GBuffers and this camera depth texture. Okay, so now we've put all of the correct colors with our various lights into our color RT render texture. But we still need to draw the skybox and the transparent objects. But we previously set our render targets to draw into the GBuffers, so we need to run set render target again so that future things that are drawn to our color RT buffer. Now there's this note here that we need to set the render target after doing the blit, because the blit will change the render targets. This doesn't make a whole lot of sense to me. Because we set the destination to be color RTID, you would think that it would leave that as the render target that it's set to, but there may be something going on behind the scenes I don't know. So let's just assume that the blit command was naughty about render targets. If you have some insight about this, please leave a comment below. Okay, so after drawing the skybox, we want to render the transparent objects. And this is rendered just the same way we rendered transparent objects in the forward rendering demo that we looked at in the previous lecture. The only thing we have here is we want to make sure we're using this forward shader tag. Now you might feel like we're done. We have the colors that we want to show the player in the color render texture. We have depth information in the depth render texture, but alas, we're not done. These are just render textures that we created and then wrote to as render targets. These are not actually associated with what is being shown to the player. So we need to copy this color information and this depth information to the buffers that are actually being shown to the player. You can reference what the player sees by this built-in render texture type .camera target variable. So we're going to write to that, that's our destination, and we're going to write to it using our CopyDepth material. Now the first argument here isn't really relevant to what we're doing, it's just a placeholder. The first argument is associated with the variable underscore main tech in your shader code, but there is no underscore main tech in our CopyDepth shader code. Instead, the source of our information is the camera depth texture. How does Unity know that we want to write to the depth texture here and not the color texture? It knows that because we use the svDepth semantic as our return variable in our fragment shader for our CopyDepth shader. Okay, we copied the depth information. Now we need to also copy the color information into the render target associated with the camera. Here, we leave out the third argument, and when you do that, it doesn't go to any particular shader you wrote. This is just a straight pass-through. It just takes whatever's here and copies it to whatever is here. So here, finally, this first argument for the source, this is actually meaningful. Okay, now we finally have all of our information displayed to the player. We're not quite done yet. These render targets exist outside of the C#.NET data management framework, so they don't get cleaned up by the .NET garbage collector. We need to explicitly release these render textures so that memory on the GPU is freed up for other uses. Now, this lecture was at the very edge of my understanding about rendering in Unity. So there's a lot that remains mysterious to me. In particular, I don't quite grok why we need to do all of this copying. Why couldn't we just directly write into the depth buffer here and use that information in our lighting pass? Why did we need this color RT buffer? Why couldn't this rendering operation write directly into the final buffer shown to the player? Why can't it directly write to the color buffer for this .camera target thing? Granted, I haven't thought about what the code for this would look like. Maybe there's no way to take this .camera target entity here and break it out into the separate color buffer and depth, but I don't know. That just seems weird to me. If you have any thoughts about this, let me know in the comments below.